Hi everyone and welcome to course number 3, E-Motor Production. My name is Moritz Stöckler and I am a research associate at the chair of Production Engineering of E-Mobility Components at the RWTH Aachen University in Germany. I previously worked in engineering department at Mercedes-Benz for several years. So much for me in person. Let's get right into it. This is module number 1, Fundamentals of Electrical Machines. First of all, we look to the operating principle of electrical machines. After that, we look at the different motor types in electric vehicles. Then we look at examples how the electric drive is used in electric vehicles. And at the end, we take a short look of the actual economic efficiency in electric motor production. So in short, this presentation shall explain the basics of and functioning of electrical machines. This presentation shall describe and explain the typical types of electric motors. And it should provide an overview of the structure of electric vehicle powertrains, both full electric and hybrids. But the first chapter is to clarify the operating principle of electrical machines. To understand how electric machines work, and electric motors are nothing else than electric machines, we need to understand the basics of electromagnetism. If current flows through a conductor, a concentric magnetic field forms around the conductor. This magnetic field has no poles, and the magnetic flux density B is directly proportional to the current strength in the conductor E and is influenced by the material via the magnetic field constant μ. If we twist the same conductor into a coil and supply it with current, the circular arrangement allows the magnetic field lines to be directed so that poles are formed. And the exist of poles and their interaction with each other is the general principle of electrical machines or motors. Now the flux density B increases with the winding density N, which is determined by the number of windings N over the length of the coil L. And how do we use this magnetism now to create a movement or torque? First of all, we know that magnetic poles interact with each other. Same poles repel while opposite poles attract. If we now build multiple conductor coils like on the page before into a stator and we supply it with current, a huge magnetic field is formed. If we applied a three-phase current and the supplied coils are changing, the magnetic field starts to rotate, while the stator as a part itself, as its name says, doesn't move at all. Other than the rotor. In this case, the rotor is built with permanent magnets into it. And when we put this rotor into the rotating magnetic field, the rotor follows it because, as we said, Same poles repel while opposite attract. And let's see how it looks like in a slow motion simulation on. We put the rotor into the stator and we see 8 pole pairs marked as red and blue. The stator poles are moving through the switching current flow. This moving magnetic field continually pulls the rotor poles toward the next stator poles that are energized. The rotor follows synchronously. Red is always paired with red and blue is always paired with blue. And we see that only the rotor as part itself creates torque and is moving. The stator is only switching the magnetic field. On this slide, we take a look at the various operating modes we can use with an electric motor. In Q1, we have the standard drive forward. The magnetic field and the rotor rotated in the same direction, forward. Now, what's different to an internal combustion engine, we are able to brake by reserving the polarity. The rotor works against the magnetic field of the stator until we stop. And we create in this way power that we can use to charge our battery. That's what we see in Q4. And the principle is the same like in an electric generator. On the left side, we see the opposite. In Q3, we drive backwards simply by changing the direction of the rotation of the magnetic field in the stator. This shows that no shiftable gearbox is required for electric vehicles for driving backwards. Like braking forwards in Q4, we can use the braking energy in the reserve braking as well to charge our battery. This process is also known as recuperation and the reason why some smaller cars use high power motors, because with a higher power I can recuperate more energy to extend my range. That's all for the operating principle of electrical machines. Next will be motor types and designs. In this chapter, we will take a look on the different motor types and designs that are used in electric vehicles. Let's start with an overview of the relevant motor types. We can divide between AC and DC motors. We can say that for automotive applications, only three-phase AC motors are relevant because of the rotating magnetic field in the stator, which we learned about in chapter 1. Within the AC motors, we can divide between the synchronous motor, where the rotor and the magnetic field of the stator are synchronized, and the asynchronous motor, in English induction machine, where the rotor follows the magnetic field of the stator with a small delay. This delay is called slip. No matter which type of motor we have, the general product architecture keeps the same. Only the axial flux motor is different, and we will take a closer look on this topology later. But we will always have some type of rotor on a shaft that is mounted to a bearing system. And we will always have a stator. Both are built in a laminated metal shield stack, which reduces the magnetic losses. We see some kind of cooling jacket, and we typically cool with oil or water. And all of these parts are built in a housing. And then we see the power electronics, which switch the DC out of the battery to a three-phase AC for the magnetic field. And we see a gearbox, even if this is not necessary. Let's start with the permanent magnet synchronous motor. We see in the structure and in the picture that we use permanent magnets in the rotor, which give this type of electrical machine its name and keep the magnetic field of the rotor permanently excited. We already talked about the function principle due to the rotor follows the magnetic field. And let's point out again that the speed of the rotor, the revolutions per minute, is proportional to the speed of the magnetic field. The advantages that we see with this type of motor is the low weight, a compact design, a high power density, and a high efficiency. Disadvantages are that the market availability of the required magnetic materials is limited, and that it has a complex mounting steps for the magnets in the rotor. We will learn about that in module number 3. This all results in a cost-intensive production. In comparison, the power density is the highest for all types of motors due to the permanent magnets. But this is coming with high costs, and nevertheless we see a high market presence of this type due to its advantages like the efficiency. Let's move on with another popular design, the externally excited synchronous motor. Again, starting on the left side of this slide, in the structure we see rotor windings. That means we use the same principle of magnetic field like in the stator with a current supplied coil. This is energized or exciting by the abrasive brushes. So in short, this design in this design, we switch the permanent magnets in the rotor to conductor coils, which are externally excited. This comes with the pretty obvious advantage to refrain from costly permanent magnets, a greater functional safety, as longer effective operation without overheating, and by that a good efficiency over the operating range. The biggest disadvantage is that a slip ring is required to transmit the electrical energy to the rotor, which causes wear and abrasion in the air gap and mechanical wear of the abrasive brushes. The more simple construction is also shown in our comparison. We have a smaller power density, but also less cost compared to the PMSM, and therefore a decent market presence for this motor design. It is used, for example, by BMW or Renault. The third popular design in the market is the induction motor. And as the name suggests, it works by induction from the stator to the rotor. We use a short circuit bars as conductor in the rotor and no coils like in the EESM. We can see that in the picture. And we supply this short circuit cage by current, with current by induction out of the stator. So the rotating magnetic field induces current in the short circuit bars of the rotor. And this generates an opposing field in the rotor, which interact with the one of the stator and generates torque. Because of the minimal time delay of the induction to the rotor is always slower than the stator. And this delay is called slip and explained why we talk about synchronous machines in the two designs before. This is an asynchronous design. In the PMSM and the EESM, the magnetic field of the stator and the rotor works synchron without any delay. The advantage coming with this design is an even more simplified construction and cost-effective production. Like with the EESM, we don't use permanent magnets and still gain a higher torque than we would do with a DC motor. As disadvantage, we see a lower power density and efficiency than with a PMSM due to the lack of permanent magnets. We have high demands on the thermal management system due to heat development in the rotor, and the induction machine is comparatively heavy and loud. Comparison is a good catchword. We see a pretty decent power density with the induction motor, the lowest cost within the three most popular designs so far, and due to that a noticeable market presence, often as a second motor in an all-wheel drive application. The next type of electric motor is the switched reluctance motor. The special thing about the SRM is that it works by using magnetic attraction between its stationary part, the stator, and its rotating part, the rotor, without needing permanent magnets or electrical currents in the rotor. The material of the rotor wants to move to a position where the magnetic path has the least resistance. And this resistance is called reluctance. So the rotor poles are attracted to align with the energized stator poles where the magnetic field is the strongest and the magnetic flux is minimal. It is the same principle like with a compass needle. As advantage, we see lower costs compared to the other designs due to the simplified construction and the lack of copper or permanent magnets in the rotor. But again, we have a higher torque than with any DC motor. Logically, the comparatively low complexity is robust in operation. As disadvantage, we see a high noise pollution and problems in torque ripple, which means that instead of delivering a smooth and steady turning force, the motor's torque rises and falls slightly during rotation. That's why we see no market presence with the SRM despite of their low costs and decent power density for a design without any magnets, either permanent or energized in the rotor. Now we need to think a bit out of the box. But first of all, the axial flux motor has the same principle like the permanent magnet motor. We use permanent magnets in the rotating part and energized windings in the stator. But the rotor is not built radial into the stator, it is built axial next to it. It works by having flat rotor and stator disc facing each other with magnetic fields running along the motor's axis. Or in other words, the magnetic field flows parallel to the axis of rotation along the shaft rather than perpendicular to it. This comes with some advantages. We gain a high torque and higher continuous output, while at the same time we can reduce the axial length and therefore lower the weight. By that, we have the possibility to add axial several stator or rotor disc to increase our power and torque. Why do we not see the AFM then in series production? So this is explained by the disadvantages. We have a complex development also caused by the high cooling requirements, and this comes with a difficult scaling in production, while we have huge unit costs. And that's why it's only in scope for cars with a low number of units and high price like Ferrari or Mercedes-Benz sports cars. So in summary, the AFM has the highest power density, even higher than the radial flux density design with permanent magnets. But this also comes with the highest cost if we not only look at the material, but also on the production costs. And this is once again the reason why we do not see this type in today's applications. But it is one of the most exciting designs for the future. To see the difference, we made a structural and technological comparison of radial and axial flux motors side by side. Starting with a structural comparison, within the radial flux motor, the rotor and stator are formed by two concentric cylinders arranged concentrically. The magnetic flux between the two components runs radial or perpendicular to the axis of rotation. Within the axial flux motor, rotor and stator have a disc-like structure, and the magnetic flux between the two components runs axially to the axis of rotation, like shown in the drawing. In a technological comparison without the limits in industrialization, we see advantages in terms of weight, a compact design, high torque and efficiency in most operating points with the axial flux motor topology. To show that and to make obvious how efficient both radial flux and axial flux motors are, we compare the different motor maps with each other. These show the number of efficiency based on the torque and the speed given in revolutions per minute. Just a quick look shows that the axial flux motor on the right side is more efficient in low and high speed with high torque at the same time. However, the radial flux motor, we see a typical shell structure and show an efficiency of 94 to 96.5% in most operating points we are facing with electric vehicles. This again underlines why it depends on the application we are facing if it is beneficial to switch to an axial flux motor or not, like in today's market. To finish on axial flux motors, I want to show you the wide variety of designs and topologies for axial flux motors. We can build it with a simple single rotor, single stator design. We could double the stator, or what we see the most, double the rotor and stay with a single stator. Or we add even more stator and rotor disc to the motor. All of them comes with different advantages and challenges whose dedicated field of applications needs to be identified in the future. Coming back to the radial flux motor designs we see today in electric vehicles. As an overview, we can divide between the permanent magnet synchronous motor, which is the most popular one due to its comparatively high efficiency and power density, despite the highest costs. The idea of the externally excited motor is to switch the magnets in the rotor with energized conductor coils with the same function but less power and the problem of wear using the brushes. Nevertheless, we see them not only in cost-sensitive vehicles, which they might be most suitable for. And we find the induction motor, where the rotor is energized by the induction of the stator. This allows us to switch the motor completely off by simply not supposing the stator anymore. We often see this topology in combination of a synchronous machine in an all-wheel drive application on one axle, the front or the rear. That's all on motor types for today. Next chapter will be some example how the electric motors are used for traction drives. On this slide, we see the basic structure with all important components for a full electric vehicle drivetrain. We can find our motors on the front, the rear, or on both axles. A dual motor concept is again not rare in the market. Wherever the motor can be found, it will always comes with a power electronic to switch the DC out of the battery to our three-phase AC for our stator. The battery is most of the time in the bottom of the car, which helps with the center of gravity and creates space in the interior or the trunk. To charge the battery, we have a charging connection like a fuel cap and onboard charger, OBC, to convert the AC of the charging station or out of the recuperation to the battery's DC. If we then combine this with an internal combustion engine to a hybrid, various operating modes are possible. It is important that we always use the e-motor to drive the wheels. So let's start on the left side, starting and driving. We see that energy or current out of the battery or an additional storage supply the electric motor, which creates torque to drive the wheels. In the acceleration mode, we add power out of the internal combustion engine to support the electric motor. In the driving and charging mode, with a hybrid vehicle, it is possible to drive and charge the battery at the same time. The combustion engine works as a generator to power the electric motor and charge the battery simultaneously. In the braking mode, the electric motor can support the brakes by switching to an electric generator and generate energy to charge the battery. Once again, we call this recuperation, and it helps the electric vehicles to create additional range. In the recovery mode, we only use the electric motor to brake the car until it stops. This is also called one-pedal drive because four-sided driving makes the brake pedal superfluous. So that are the different operating modes, and they are determined by the energy management strategy, which always attempts to maximize the range with our electric vehicle. Anyways, we have different ways to use the internal combustion engine and the electric motor in hybrid applications. In a serial hybrid application, that is what we see on the slide before, the internal combustion engine generates electricity, and only the electric motor drives the wheels. In a parallel hybrid application, both the internal combustion engine and the electric motor can be used to drive the wheels directly. And the power split hybrid combines both methods. Depending on the situation, the internal combustion engine can either charge the battery or drive the wheels together with the e-machine. And this always aims toward that the internal combustion engine works in the most efficient operating point. In all electric vehicle, we can divide between a central drive with kind of differential between the motor and the wheels, or single wheel direct drives. The most common one is the central drive without any gearbox. This is given by the possibility to integrate this easily in the old combustion engine platforms of the car manufacturer. We see newer cars coming with a maximum of 2 gears to help the electric motor to always work in the most efficient operating point. If you remember back on the motor map diagram, on the slide we compared the radial flux motor and the axial flux motor with each other. There are some startups that work on direct-to-wheel application, for example with wheel hub motors, where the rim works directly as the rotor. But from today's perspective, it is not expected to be successful. If we look to a central drive, we have many objectives to integrate more components to a, let's call it, one-part electric drivetrain. With this, we gain greater efficiency. We are able to improve the driving characteristics. We are able to reduce the costs and the weight, both very important for electric vehicle, by a reduced number of parts and wiring harness. And maybe the most important thing, we make the electric motors more scalable due to the modularity. Summarizing, the reduced volume of the integrated drivetrain supports the switch from conventional vehicle architectures and characteristics towards new vehicle and mobility applications. But electrification also works in other sectors, not only for cars, like the agriculture. We see electric trucks in the transportation sector. I can recommend to Google for the e-Actros from Daimler Truck. Very cool. And we also have the power with electric motors to drive construction machines as well. And all of this without a fundamental change in all of this application due to the simple design of the electric motor and its compactness, which make it very easy to adapt in all of these vehicles. Now, to finish this lesson, I want to present you some numbers of the economic efficiency in electric motor production. First of all, we want to check if we can believe the hype. For this, we compare an optimistic forecast out of 2018 with the reality and see that both are in line with each other. So in 2023, we have approximately 42 million electric vehicles worldwide. And this number is expected to grow to more than 200 million by 2030. This corresponds to a growth rate of more than 500% in 7 years. So that we can say that the number of electric vehicles worldwide is in line with the optimistic forecast of the past, and that there are no signs of a crisis in electrification. If we look at the car manufacturer or OEMs in the actual market environment, we see that Tesla and BYD out of China are dominating the market of full electric and plug-in hybrid cars. Other, mainly Chinese companies, have a share of 19.5%, and only when we put them together, we see the two biggest internal combustion engine companies with Volkswagen and Toyota, both with a market share nearly above 4%. And it is expected that European and Japanese manufacturers will have problems to catch up and play a subordinated role and are coming under increasing pressure by Chinese manufacturers. This statement is confirmed when we take a look at the best-selling vehicles in 2023. The best-selling car is the SUV Tesla Model Y, followed by the Model 3, both using an induction motor and a permanent magnet synchronous motor and resulting high power. But also with a higher price point at 40 to 45,000. The following Chinese cars are all at a much lower price point, around 10 to 20K, which is only half of a Tesla. And when we look at Europe or companies like Mercedes-Benz or BMW, the prices are up to 4 times higher than the cars out of China. To bring this together with our second chapter and take a closer look at the used electric motor topologies in the market, we see no clear trend that can be derived with regard to the preferred motor topology for electric drivetrains. The PMSM continues to dominate, but the EESM and the induction motor are used both as support and main drives. Regardless of the motor topology, the hairpin design has become established for this data. How a hairpin stator looks like and how it is produced will be part of the next module of this course, so stay tuned. If we take a look at the value creation structure on this slide, mainly for companies out of Europe, the USA or Asia, we see that OEMs like Volkswagen, Tesla, Porsche, or BYD increase their vertical integration by starting to produce the electric motors and their single components by themselves, and not doing only the final assembly of the electric motor or only the final vehicle assembly where the motor just comes in time from the supplier like in the past. Despite that, we still have many companies listed on the left-hand side that produce components like the wire or the sheet metal stacks. On the right-hand side, we see some popular names of companies that are responsible for the mechanical and plant engineering, or in other words, companies that build the machines to build electric machines for traction drives. That's all. Let's summarize what we learned today. In this lecture, the assemblies, housing, shaft, bearing system, laminated stack, and rotor-stator assemblies are presented as generating basic components of electric motors. In this lecture, the current relevant traction motor topologies in automotive applications were presented. In this lecture, the possibilities for the use of electric motors in different drive architectures were explained. Okay, Thank you for your attention. I'm looking forward to see you again in the next module, Data Production. Goodbye.